So, so any quick questions on the homework before we get started? Okay. So let's go ahead and talk about some stuff. So like I said, here's my, or not my website, here's Pavel's website. And here's all the blank outlines, and here's all completed ones, and related video lectures, and as well as any quiz solutions input. So let's talk about the quiz solutions, shall we? So, yeah, wrong. Okay, that's too much. All right. Okay, so the first quiz was basically just a couple of basic antiderivative problems. So the first one was evaluate the antiderivative integral of 7 times dx minus 8 times secant times tangent. So this one wasn't too bad. A couple common mistakes I did see though were making sure to know the antiderivative of secant times tangent, that is secant. And then remembering, because this is an indefinite integral, you do need to include plus c. Some of you lost points on that, so keep that in mind. So the next thing I wanted to talk about was finding the area of the region bounded by the following equations. We have this guy right here, this function of x, and we have y equals 0, which corresponds to the x-axis. We have x equals 1 and x equals 4. So these will correspond to your upper and lower bounds. Sorry, your lower and upper bounds respectively. So as a result, you should then say, okay, the area can then be expressed as this integral here. And I tried to set everything up so that way you don't need a calculator. So because of that, what I mean is that the antiderivative is just this. So the calculator is not necessary at that point. And because we have fairly nice numbers, 1 and 4, which have nice square roots, we can then say, all right, if we apply the fundamental theorem and simplify as necessary, we then have 4 to the power 3 halves. Well, that's just 8 because of exponential properties, and noting that 4 to the power 1 half is 2, so then cube that gives you 8. And then, of course, 1 to any non-zero power, well, I guess 1 to any power is 1. So that gives you that, and then you should end up with a nice middle number of 16. Okay? Cool. Questions on that? All right.
I have a question.
I hope I have an answer.
For the first one, for future reference, if we would use the other, like, if it was a -8 over cosine x, would that be the same thing?
Negative 8 over.
Secant squared, or secant is 1 over cosine.
Like, this would be the same thing.
Yeah, I was just asking because
Oh, so like 8 over cosine?
Yeah.
Oh, yeah, no, this is fine. I'm just saying, like,
I
as long as
in
it's,
the future.
yeah, as long as the answer itself is correct, it doesn't matter. I just threw it in form secant because, that's how we know the antiderivative of secant times tangent. Okay. Any others? Okay. All right. Okay. Good. Okay, thank you. All right. So let's move on to the class for today. So lesson 2. Thankfully, there's not really any new concepts, well, yet anyway. So let's go ahead and do a couple of examples that are mostly just continuations of what we've been doing up until this point. Also, quiz 1 statistics, average was a 7.47, median was an 8. Quiz 2 is next Friday, so next time, covering lessons 1A and 1B. Quiz 3 is going to be covering lessons 2 and 3 next Wednesday. So today's lecture as well as next Friday's lecture. Okay. So with that out of the way, let's move on to integration by substitution 3. So like I said, not a lot of new examples, so let's just go ahead and continue from where we left off, so to speak. So suppose the height of an alien plant increases at the following rates. So we have h prime equals 1 over square root of t times q root of 1 plus root t. And this is in t in hours since 6 a.m. Now, the question asks us to figure out how tall does a plant grow from 7 a.m. to 3 p.m. and rounded to 3 decimal places. So one thing to note here is that, well, first off, we should actually figure out, well, what are our bounds here. So we note that if t is an hour since 6 a.m., we should be able to translate these two times given to us pretty quickly into their respective values of t. So 7 a.m. will correspond to t equals what? Just, yeah, t equals 1, right? So nothing too crazy with that. And then t equals what with 3 p.m.? So if at 3 p.m. t equals what?
9.
Yeah, t equals 9. Good. Okay? So then what you notice is that we're going from t equals 1 to t equals 9 here. So you're looking at this function here, you notice that this function is always going to be positive on that interval, right? So basically because there are no values from t equals 1 to t equals 9, at which this becomes negative. So as a result of this, this h prime of t is always positive. So that means that remember, if we have a positive derivative, that means we have an increasing function. So that means the height of the plant is always increasing, so that means the plant is always growing, right? So because of this, how tall does a plant grow? In this case, this directly corresponds to the change in height. Okay? And so as a result of this, we can then say, all right, we're ultimately trying to figure out the difference of h of 9 minus h of 1. Okay? So the nice thing is that if we have a derivative of this function where we're trying to figure out the difference of two of its function values, and we're given its derivative, how can we use a fundamental theorem of calculus to express this difference as an integral? Yep. So the lower bound should be 1, the upper should be 9. And then of course the integral we're trying to take the antiderivative of should be this guy, right? So we have 1 over root t times the cube root of 1 plus root t dt. Okay, so because of the title of today's lesson, well, that should be a pretty good indication that we need to utilize some sort of u substitution, right? So taking a look at this function that we've got here, what would you want to let u equal here? Yeah, 1 plus root t. That's a good option. Okay, and what happens if we do that? So we notice that if we take the derivative of both sides, then we have du equals what times dt? Yeah. 1 over 2 times the square root of t dt. And we also rewrite this as dt equals 2 times the square root of t times du. Okay? And then also one thing to note here is that because we have a definite integral, we also need to change the bounds accordingly, right? So in this case, if we have t equals 9 and t equals 1, that means we need to have the corresponding u values, which end up equaling what? So if t equals 1, then utilizing this u substitution up here gives us that u has to equal what? Yeah, it's 2, right? Because we have 1 plus the square root of, well, t equals 1, so we just have 2. And similarly, let t equal 9 up here to get its corresponding u value. To get 1 plus the square root of 9 equals, in this case, 4. So in this case, that'll get you the integral from 2 to 4 of 1 over the square root of t times the cube root of, in this case, 1 plus root t, which we have established to be u. And then dt is then, well, 2 times the square root of t du. Okay? So then what you notice is that, well, these root t's cancel each other out pretty nicely.
And so what we're left with at the end of the day is the integral from 2 to 4 of 2, from this 2 right here, and then over the cube root of u du, which we can then rewrite as the integral from 2 to 4 as 2 times u to the what power? Yeah, negative 1/3, right? Du. Okay. So then if we were to utilize the antiderivative power rule on this guy, what should we end up with? So we're going to have 2 times, well, from this 2 up here, and then times what? So first off, we would have, by the antiderivative power rule, we would have u to the what power? 2/3, right? Okay. And then we then have to multiply essentially by its reciprocal, which ends up becoming 3/2, right? Going from 2 to 4. Okay. So then if we apply the fundamental theorem of calculus on this guy, we should then get, let's see, well, first off, these two cancel each other out. And then we have 3 times 4 to the 2/3 minus 3 times 2 to the 2/3. Okay? And unfortunately, there's not really a nice way for these to simplify beyond this, so unfortunately at this point, we just have to plug this into a calculator and go from there. So plug this into a calculator, and you should end up with 2.797. And because of our units up here, we should then get that our height also has to be in centimeters here in this case. Okay. So that's example 1. So any questions on that one? Okay. So that's example 1. So thankfully example 2 is going to be very, very similar once we figure out what's going on. So example 2, so we still have the same, we have this plant that still grows at the same rate, but now we're just saying it just T hours after it was planted. So we're not necessarily saying said 6 a.m., we're just saying T hours after it was planted. How tall does a plant grow during the 3rd hour? And we need to round our answer to 3 decimal places. So in this case, well, we still have a rate function, so we still got to take the antiderivative of this with respect to t. So we still have 1 over square root of t times the cube root of 1 plus root t dt. But then you guys, well, wait a minute. Well, what are our bounds in this case? So what are these? What goes in these 2 blanks? So we got to figure out what this integral here is. So let's draw a little bit of a line chart to see where we're going with this. So here's t. So I'll put t equals 0 here, and then 1, 2, 3, 4, and 5. Okay? So here's what you notice. So if we go from t equals 0 to t equals 1, that encompasses the entirety of the 1st hour, right? So I'll call this h1 for short. And then from t equals 1 to t equals 2, that's the 2nd hour, right? And then so on and so forth. So then if we were to try to figure out the bounds of the 3rd hour, what would those be? So the 3rd hour goes from t equals what to t equals what? From 2 to 3, right? So h3 is this guy right here. So we're going from 2 to 3. Right? So basically what you realize is, okay, well, we still have the same function we're trying to take the antiderivative of as the first example. The only difference is the bounds. So aside from that, that's basically it. So I'll definitely be skipping a few steps here, of course, because a lot of it's similar to the first example. But I will note the change in bounds. So only change from example 1 is the bounds. So in this case, t equals 3 and t equals 2. So because we're still dealing with the same function here, we're still going to have the same u substitution. So with t equals 2, we should have the corresponding u value have what as its exact value? Yep, 1 plus root 2. And then similarly, t equals 3 gives you u equals 1 plus the square root of 3. Okay? So then from there, what you notice is that, so we still have, okay, scroll a bit more, there we go. So what you notice is that if we work with just this part, well, all this becomes is this part up here, which we already established. So this equals, well, so we have 2 to the u to the negative 1/3 du, but then our bounds become 1 plus root 2, and then 1 plus root 3. But other than that, it plays out the exact same way as example 1. So if we apply if we take the antiderivative, we end up with, still have 3 times u to the 2/3. So then apply fundamental theorem, you end up with 3 times 1 plus root 3 to the 2/3 minus 3 times 1 plus root 2 to the 2/3. Okay? Because it still plays out the exact same way. But other than that, plug that into a calculator, you should have 0.464 centimeters as your final answer, rounded to 3 decimal places. Okay? Okay. So, questions on that? Good? Nay? Somewhere in between? What's somewhere in between?
Sorry, I'm just trying to catch up. I got lost somewhere around the. Oh, never mind.
Okay, cool. All right. Any other questions? Okay. All right, I'll give you guys a second to write all that down. Okay. All right. All right. So let's go ahead and move on. So, example 3 now. So we're saying suppose as a particle slows down, its velocity is given by v of t equals 2 times e to the 1 minus t minus 1 centimeter per second. So we're saying that if the particle starts slowing down at time t equals 0 seconds, find the distance it takes for the particle to stop. Okay? So one thing that the problem doesn't really explicitly say, but I'll just say anyway, is that the problem wants you to assume s of 0 equals 0. Okay? And the reason I say this is that because not only does it make our computations easier, but log capital will want you to do this as well in the homework. So just keep that in mind. All right? So the first question we should be asking ourselves is this. So if the particle starts slowing down at t equals 0, we need to figure out how far does it go before the particle stops. So the first question we should probably be asking ourselves is, okay, well, when does the particle stop? That's probably one question we should be asking ourselves. So when does the particle stop? Okay. So in order to do that, well, we note that we have a velocity equation given by this guy right here. So if we want to figure out at what time does the particle stop or become motionless, then that means we need to take our velocity function and then do what with it? Yeah, just set it equal to 0. So our goal, or at least the first time, is solve for v of t equals 0. Because then that'll give us our time at which the velocity is 0. So if we do that, we have 2 times e to the 1 minus t minus 1. Set that equal to 0. So let's go ahead and start by, taking this bit by bit in solving for t here. So what I mean is, let's go ahead and first solve for the exponential. So we have e to the 1 minus t. So that should pretty quickly get you that this exponential using a quick bit of algebra is what? Yeah, just 1/2, right? Nothing too crazy with that. Okay. So then, if you want to, now we have e to the 1 minus t here. So if we want to get rid of that e somehow, what should we do? Natural log. Good. So natural log both sides. So we have 1 minus t is then equal to natural log of 1/2. And then a quick bit of algebra later should then get you that t is then equal to 1 minus natural log of 1/2. Okay? So that's when the particle stops. Or at least that's the exact value. So we then say, okay, now from this we can say given, so we have that s of 0 equals 0, and we also have something else. So if s of t equals the position function, then if you recall from last time, what's the relationship between the velocity function and the position function? Derivative, right. So s prime of t, take a derivative of position to get velocity. So we have s prime of t equals 2e to the 1 minus t minus 1. Okay, so we're given this. And so basically now all we have to do is figure out, well, where does the particle stop? So essentially we got to figure out s of 1 minus natural log of 1/2. Okay? So in doing so, we can then say, all right, well, we're trying to figure out this value here, but we're given s of 0 as well as the derivative. So if you recall from last time, there was a trick that we used to be able to do that without having to find the actual function s of t. Do you remember what we did? I think it was example 3, I think it was, or one of the earlier examples from lesson 1b. Yeah. What's that? In terms of which one? Well, yes, we do need to use substitution, but
you solve for the derivative between 0 and your t value, and then you add your s of t initially.
Exactly. We had to use fundamental theorem, right? So what I mean is that we have s minus natural log of 1/2, because that's the thing we're trying to find, and then minus s of 0. And by fundamental theorem, this is equal to the integral from 0 to 1 minus natural log of 1/2 of s prime of t, which is 2e to the 1 minus t minus 1 dt. Okay? And then noting that s of 0, well, that's just 0 by assumption. What that says is, okay, if we want to figure out this guy, all we got to do is figure out this integral, and then we're done. So let's go ahead and do that. So, based off of the title of today's lesson, we should be using a u substitution. So what do you think we should be utilizing for our u substitution here? 1 minus t. Good. Good. So that means du is then equal to dt times what? Yeah, -1. So we have du equals negative dt, or you can also write this as dt equals negative du. Okay? Okay, so again, because we have a definite integral here, we should correspondingly change the bounds. So we have t equals 1 minus natural log of 1/2, and t equals 0. So utilizing our u substitution that we have up here, well, if you let t equal 0, that's, well, pretty quickly that's just 1 for our lower bound. But then what does the upper bound become? So the upper bound will become what? So if t equals 1 minus natural log 1 half, then u would equal what? Yeah, just natural log 1 half, right? So then we have the integral from 1 to natural log of 1 half of, let's see, 2 times e to the u minus 1, and then minus du, because of this guy right here. So this ultimately simplifies to, let's see, integral from 1 to natural log of 1 half of, in this case, if you distribute the negative to both terms in here, you have 1 minus 2 times e to the u du. So, if you then take the antiderivative of this with respect to u, then what should we get as our answer here? What's our antiderivative with respect to u? So first off, what would be the antiderivative of 1 with respect to u? What's that? Well, antiderivative. Yeah. Well, u in this case, right? U, yeah. But yeah. And then minus 2 times so what's the antiderivative of e to the u? It's itself, right? So then we have 1 and then natural log of 1 half is our bounds. So then we just apply fundamental theorem and then go from there. So we have let u equal natural log 1 half. So we get natural log 1 half minus 2 times e to the natural log of 1 half. And then minus, let's see, oh gosh, what are the, okay, yeah, that became 1. Yeah, never mind, we're good. Sorry, a bit of a freaked out for a second there. Never good. So let u equal 1, then we get 2 times e to the 1. Yeah, okay. We're good, no worries. Yeah. Okay, so let's see. We get natural log of 1 half, so that's our first term, and then minus 2 times e to the natural log of 1 half. So what does that simplify to? What was it? Yeah, just 1, right? Because you know that's, well, e to the natural log of 1 half, well, that's just 1 half, right? But then multiply by 2, and then you just get 1. Okay, and then you distribute the negative to both terms here to get 1. You get negative 1, and then plus 2 times e to the positive 1. So ultimately, this simplifies to natural log 1 half minus 2 plus 2 times e to the first. So if the problem just asks for the exact value, you could leave it as this and move on. But if you want to put it into a calculator, you should end up with 2.743 and then centimeters. Okay? Okay, so this ultimately becomes your final answer here, because this is what we were trying to solve for from the beginning. Okay? Yeah?
I plugged in the calculator and natural log of 1 half is a negative. Does it matter that it's like less than like that's?
Yeah, so that just means that this contributes to the negative component of your answer. So this would be like, 2 times e to the 1 and then something negative here, something negative here.
Okay. Thank you.
Okay. Any other questions? Yeah?
Why did the lower limit become 1?
So if like t equals 0 and here, you get 1.
Oh, okay.
Okay. Any others? Okay. So let's move on to the, well, I shouldn't say brand new concept, but not really something you've seen before, so I guess it could qualify as a new concept depending on how you view it. So, the next concept I want to bring up is the idea of an average value of a function. So, before I tell you what the formula is, let's go ahead and give some intuition for this. So let's say we have integral from a to b, integral from a to b. So let's say we want to focus on have this function and say, all right, well, if you want to focus on the area of this shaded region here, well, we all know that's the integral from a to b of f of x dx. Okay? So now let's instead say, all right, well, we still have the same bounds, but now let's say we want to find, some constant or some number such that if we were to take the area of this rectangle here, and this rectangle here, we should get the same area as this guy right here. So I'll denote this as f sub avg for reasons you'll see in a second. So the idea is to say, all right, if we take the area of this rectangle, that is this constant f sub avg, times b minus a, the length of your integral, we want to be able to find this constant f sub avg such that these two quantities are the exact same. Okay? So what that tells you is that if you want these to be equal to each other, then what that tells you is, all right, if you want to figure out what this guy is, then that should probably tell you that we need to divide b minus a over to the other side. So, as a result of this, that should tell you that this f sub avg, which, as you might have guessed, corresponds to the average value of f of x, is f sub avg equals integral from a to b of f of x dx over b minus a. Okay. So that's the intuition behind the average value function, if you want to think of it like that. Okay? And I'll also write this down here as well, closer to our fourth example. So we have f sub avg equals integral from a to b, f of x dx over b minus a. Okay? So the reason why I'm focusing on this is because, well, not only will you see this on the homework, but there are also some interesting applications to this. So before we get into them, let's focus on example 4 first. So we need to find the average value of 6x squared plus 2 over the interval 1 to 3. So in this case, well, we are given the function and we're given the interval of consideration, so we can just plug them into our formula here and go from there. So in this case, f sub avg will be, in this case, the integral from 1 to 3 of f of x, which is 6x squared plus 2 dx. And all over, well, the length of the interval, which is, in this case, 3 minus 1. Okay? So, all right, nothing too crazy so far. So in this case, this can be rewritten as 1/2, because 3 minus 1 is 2, times the integral from 1 to 3 of 6x squared plus 2 dx. So then if we were to then distribute the 1/2 into the integral here, well, then you should be able to pretty quickly see that this is just the integral from 1 to 3 of 3x squared plus 1 dx, okay, which thankfully has a pretty nice antiderivative of what? I think I heard from someone. What was it? So x cubed x. Good. Okay. So the antiderivative of this is x cubed plus x. So going from 1 to 3, we then apply the fundamental theorem of calculus, which then says, all right, let x equal 3 to get 3 cubed plus 3 minus let x equal 1 to get 1 cubed plus 1. Okay. So then you go ahead and clean everything up, and then you should end up with a fairly nice number of 28. Right? So that's example 4. So nothing too crazy yet, but any questions on any of that? Yeah?
Was f of a would be just the length of the rectangle in the previous diagram?
Here?
Yeah, is it just the length of the rectangle or?
Yeah, so in this case, yeah, that'll correspond to your length. Oh, no. They will correspond to your height.
Oh, okay, sorry.
Yeah. The b minus a part is your length. So I'll go ahead and put that here as well. So, height. Okay. Okay. Any other questions on page 3? What's up?
Once you become length, do you then multiply by the 1/2?
Well, we already did multiply by 1/2 by throwing the 1/2 in here. 1/2 times all this is just 3x plus 1. Okay. Any other questions? All right. So, all right, nothing too crazy, but now let's spice things up a bit. So now what we're going to do is throw one of the harder questions into today's homework at you. So, suppose another alien plant is shrinking at the rate of -100 times e to the -5t. If the plant has an initial recorded height of 300 centimeters, find the average height of the plant 4 minutes after this initial recording. And round your answer to 3 decimal places. All right, so this one's going to be fun. Here we go. So, a couple things we need to look at here. So h prime of t is given by this. Okay, fair enough. We also have that the plant has an initial height of 300 centimeters. So if we denote h of t by our height function, then what should that tell you? What should this bit of data tell you about our initial condition to us? So h of what equals what? Yep, h of 0 equals 200. Good. Okay. So now there's one more thing we need to look at here. We need to find the average height of the plant 4 minutes after the initial recording. So we need to be careful here. So I'll put this in red and in all caps just so we are on the same page on this. So the thing is that we need the average height, which is modeled by h of t, over the first 4 minutes, that is the interval 0 to 4. But we're not looking for the average of h prime of t. So need to find h of t first. Okay? So that's our first goal in this problem. So once we figure out h of t, then we can take the average of that function over our interval as needed. But that's one thing you got to be careful with these types of problems. So make sure to know what you're looking for here. All right? So given our data, it looks like, okay, well, we got some data that looks like we could set this up as an initial value problem. And thankfully, because we're trying to figure out h of t, we can do exactly that. So let's first start by finding our general solution. Okay? So h of t, well, we just have, the first thing we got to do is take our antiderivative of h prime. So integral of -100 times e to the -5t dt. All right? So in this case, we say, all right, so based off of what we've been doing up until this point, what will be a good u substitution for this problem? -5t, good. Okay, so then from this you should be able to pretty quickly see that du is then -5 dt. or if you prefer, dt equals du over negative 5. Okay? All right. So now, what do we get? So we have the integral of negative 100 times e to the u times du over negative 5. Okay? So from this, we can say, all right, this simplifies pretty nicely to just 20 times e to the u du. So what do you notice? Okay, well, this has a pretty nice antiderivative of, well, 20 times e to the u, as per what we saw in, what would it be, example 3. But then, because this is an indefinite integral, it's 20 times e to the u plus c, right. Good, make sure to remember plus c in case a quiz or the next exam covers this. Or, in particular, the next quiz, hint hint. Just gonna leave that out there for no arbitrary reason at all. All right. Okay, so because our original variable is in terms of t, well, we got to bring everything back in terms of t. So we then have 20 times e to the negative 5t plus c is our general form of the height function. So we then say, all right, so we have a general form, so now let's use our initial condition to figure out what is this particular solution here. So if we let t equal 0, we end up with, all right, so 20 times e to the, well, times e to the 0 plus c equals, well, in this case, so noting that e to the 0 is, everyone, 1, 2, 3, 1, good. 20, so we ultimately get that the first term is just 20 plus c, and then that's all equal to, by our assumptions, 300. Okay? So that would imply that c, well, that should be 280. So that therefore implies that your, well, I'll put it down here, that therefore implies that h of t is then equal to, well, 20 e to the negative 5t plus 280. Okay, so now the good news is that now we have h of t, which is exactly what is the first thing we needed to do. So now we can take this function and then find the average height of this guy over the first 4 minutes. So in this case, we have the thing we were trying to look for here. Okay, so now find average of h of t over 0 to 4. Okay. So we then say, okay, so now from here we apply our average value formula. So in this case, I'm going to use h sub avg because in this case, h is our function in this case. So we have the integral from 0 to 4 of, well, h of t, which is 20 times e to the negative 5t plus 280 dt. All that divided by the length of the interval, that is 4 minus 0. Okay? So let's go ahead and clean this up a bit to see what we get out of this. So here what we notice is that, well, 4 minus 0, well, that's obviously 0. But, so then from this we can say, all right, so this is something all over 4. So if we bring this division by 4 into our function in here, what does that simplify to? What's that? Yeah, so we're essentially multiplying this function here by 1/4, right? So what would that simplify to if we did that? We distributed 1/4 to both of these terms. Plus 70. Good. Okay. dt. Okay. So then now, let's go ahead and take the antiderivative of this thing. So here, well, the antiderivative of this, as we already saw, was, well, or by similar reasoning to what we've already saw, is just 70 times t, and then going from 0 to 4. But if we use similar reasoning as to what we did in the first sort of half of this problem, what would the antiderivative of this first term be? Using similar reasoning as in the first part of this problem. Exactly. And let me explain why that is. So, or let me explain briefly why that is. So if we take a look back at what we did up here, the antiderivative of negative 100 times e to the negative 5t ended up being 20 times e to the negative 5t. So based off of what we did here, all we really ultimately did was just divide our original function by negative 5. So if you utilize similar reasoning that we had up here and we apply it to here, well, then you realize that all we really have to do is just divide this thing by negative 5, and that will be our antiderivative. So, okay. Yeah?
For something like that, will it always be negative 5, or is it whatever the power is?
Well, in this case, since we have just some constant times t, that's when it would play nice and natural. It doesn't always do that. It's especially if you have something that's not linear. The only reason I just said divide by negative 5 here is just because of the similar work we already did up here.
Okay. So then from here we apply fundamental theorem. So then we have, well, negative e to the negative, in this case, 20. And then plus, well, 70 times, in this case, 4, which ends up being 280. Then minus, so let t equals 0 to get negative e to the 0. And then plus 70 times 0, which is just 0. Okay. So from here we say, all right, then we distribute the negative to get plus e to the 0, or just 1. So ultimately we have negative e to the negative 20th plus 280 plus 1. Okay? Now, what you notice from this is that, well, if you plug negative e to the negative 20th into a calculator, that's pretty hecking small. And this is the only time I'm going to let my phone out in class, so I'm just going to show you how small it is. Yes, 2.06. It's kind of hard to see, but it's supposed to say 2.06 times 10 to the negative 9th, which is really hecking small. So if you're trying to round to 3 decimal places, 281.000 is the best you can do. And of course, this is if we take a look at our original units of the problem, which is height is centimeters. So that should tell you that your final units have to be in centimeters as well. Okay? And that's example 5. Okay. Any questions on any of that? Yes?
Sorry, back when it was the 5e minus 5 to the power of minus 5t, and we found the antiderivative, why didn't the power change?
Because so in this case, I'm just utilizing similar reasoning as what we did in the first half.
Okay.
So if you recall, it ultimately stems from the fact that the antiderivative of e to the u doesn't change, so the power doesn't change.
Oh.
Okay. Any other questions on example 5? Yeah?
think if it doesn't say, if it doesn't say otherwise, you can assume it has to be equals. All right. If I don't see any other questions, I'll see you on Friday with the. I'll bring back the first quiz I'll bring back the first quiz and I'll give you guys the second quiz next time. Sound good? Sound good. Cool.